Okay, so we're going to talk about the textbook. The textbook splits these up. Okay, so make sure you pay attention. Go to page 31. Okay, you're all on 31. So 5.5, sorry, the book calls it conditional probability. So it's 5.5 and 5.6. I'm doing them both at the same time because I find that if I do them separately, students they miss the point. But you can actually do them side by side to understand when are events independent, when are they dependent. Okay. I'm just going to give you a short demonstration here. If you're flipping two coins, right? Me flipping the first one, will that have an effect on what the outcome is of the second event? No, it will not. So that's a classic. When you have dice, for the most part, there's going to be a bit of a twist to it, but for the most part, dice, coins, and stuff like that, there's nothing you can really do to affect the. You can do one over the other. Doesn't matter which order you do them in. One event will not affect the second. Okay, so that is important too. That's basically the definition of independent events. Dependent events is I don't have a deck of cards on me, but if you're thinking of marbles or cards in a deck, if you take one out, like if I walk around and I say, Isabel, take a card. As soon as she takes it and she keeps it, she doesn't put it back, and I go over to this Robert, I say, hey, you pick a card. The probability has now changed, right? Because there's fewer cards left. So that's in a nutshell the difference between the two, where the independent events, nothing really affects the second outcome. You can do 4 coins, first, second, third, fourth. It won't matter. But if you compare that to dependent events, that's when the universal is being affected. So I will introduce to you tree diagrams. I like tree diagrams when you do probability, and I will show you how I do that. It's not always necessary, but sometimes I will ask you to do it. Okay, there are instances where you're going to need to do it to answer it correctly. Okay, so here we go. Two events happen either simultaneously or in a sequence. So it doesn't matter if you do them both at the same time or in a sequence. And it does not affect the total number of possible outcomes. Right? Events are called independent. So, for example, what's the probability of rolling a 5? Right? Rolling a 5 and rolling a 3 is 2 6-sided. Okay, dice. If you consider these two events, the outcome of one does not affect the other. Consider the following tree diagram. So here we go. So I'm going to write this in words. Rolling a 5 is the first branch. Not rolling a 5 would be the second branch. So I'm considering the first event. Okay, so rolling a 5 is 1 out of 6. Not rolling a 5 is 5 out of 6, right? So we understand that. Then on the second event, I will say 3, and not rolling a 3 would be here, and same thing here, 3 and not rolling a 3 would be down here. Okay, so you're always going it, not it. That's how, when you're doing probability, you want to kind of branch off like that. So it's not quite, it is still an outcome tree, but we're considering it happening, it not happening. That's where we're branching off into. Okay, so you won't have the total number of possible outcomes at the tip of your branches in this case, and instead we're going to consider the probabilities. Okay, so rolling a 3 would be 1 out of 6. Not rolling a 3 would be 5 out of 6. Rolling a 3 is 1 out of 6, 5 out of 6. As you can tell, in this case, we're using both the same universal dice, but it could be a 4-sided die and a 6-sided die. So just remember that this can change. In this case, I chose 2 standard dice. Okay, so in this case, the probability of getting a 5 and a 3 would be what? In math, if you're saying this and that, can we go over here to and do this? Okay, it's and, it's intersection. It's both. Okay, how do we come up with that probability? We multiply them. You multiply the first and the second. So we're taking both these probabilities, you put them down. What do you get? What's 1 over 6 times 1 over 6? Any brave volunteer? What's your denominator? 6 times 6, which is 36, right? Keep going. 1 for this branch here, where you get a 5 and not a 3. The probability of not getting a 3 is 5 over 6. So 1 times 5 is 5. 6 times 6 is 36. I will not reduce here on purpose because it gets pretty ugly later on. Okay, the fractions get pretty ugly. Let's follow this branch. So you're not rolling a 5, but you're rolling a 3 would be 5 over 6, right? This one here, times 1 over 6. That's still 5 over 36 when you're multiplying them. This is not or, this is and. So we multiply. The last one is 5 over 6 times 5 over 6. That would be 5 times 5 is 25 over 36. Okay. So what did we just do here? Well, let's write down what we just calculated. This here is the probability of rolling a 5 and rolling a 3. That's what you just found here. This would be the probability of rolling a 5 and what do you go down this branch? Not rolling a 3. This would be probability, I'm just going down the branches, not rolling a 5 and rolling a 3. And this last one is probability of not rolling a 5 and not rolling a 3. Okay, so that's what you're calculating. We can go equals like this. It's okay to do that here. Okay. Which one are we right now interested in? This question is specifically interested in this one right here. Okay, rolling a 5 and rolling a 3. But you always have to remember that there are these other branches that are there. They're still in the background that make the other events, right? But we're just interested in this one. Okay. So this, I'm going to circle that. That's the one we're interested in, right? Answers the question, right? So it's 1 over 36 chances of that happening. Okay? All right. Let's keep going. I'm going to go to the back side. I left, why is the bottom half blank? If I need to do another example tomorrow, I have that available, okay? Let's keep going. Let's consider dependent events. And you know, did you know that it takes a long time to publish a book? Right? If you make a book, it gets edited and edited and edited and proofread and right. And now I know why, because it doesn't take much to make a mistake on a booklet like this, right? If the first event affects the second and so forth, we call them dependent events. Okay. Consider a standard deck of cards. Geraldine draws one card, does not replace it. I will not put this in bold normally in a test, on a test or quiz AC, but here it is. It's not being placed back, no replacement, anything like that. keyword. You're like, ah, we're talking dependent events. One is affected by the other. Then draws another card, right? What is the probability of drawing an ace and a face? Okay, so I'm just gonna highlight them differently just so you see, right? There's your ace and the face, right? So those are the two events that are happening here. And I like the tree diagram for the following reason. The first event, by the way, guys, it doesn't matter if this question had said drawing a face and an ace. It doesn't matter, right? That doesn't matter. You would ultimately have the same final probability, okay? But let's just go ace here, and this would be not ace. Mr. Dirksen, what does it mean not ace? Well, any card that is not an ace, right? That's basically, like, it could be a queen, it could be a 5, a jack, anything like that, right? So how many aces are there? 4 out of 52, right? Therefore, how many non-ace cards are there? And I want you to always subtract, right? Take away 4 from 52, you're left with 48. So no surprises there, I think, right? Now, what's the second probability we're trying to figure out? Face, right? Can I just, I think I can go face, not face, and then I'll just go F, not F. Okay? How many cards are left? It has this card, one card has been drawn. These are just the probabilities, but one card has been drawn, not replaced. So we're down to 51. And that's what I want to highlight today. Okay. So I think I'm going to go, I haven't used, so I want to highlight the 52. And I want to highlight the 51s. So if you see a tree diagram and you notice, oh, wait a minute, the universal is changing, right? These are dependent events for sure. So let's fill in the numerators for this thing because it's also interesting here. So let's consider the ace has been drawn. How many face cards are left? Or how many face cards are there? Because the first one was an ace. So you still have 12, right? What would this number be here? I always tell you to subtract. You go 51 minus 12, right? So I'm going to go, I don't want to make this too busy here. 51 minus 12, that's what's going to go in there, so 39. Okay. And then up this branch here, this would be 12, right? 12 faces, unless they had said that there was a face card drawn first. We consider this 12. And then this is 39 as well. Okay. So there you have your branches. So the first one here, let's calculate. To get an ace and a face, that's 4 out of 52 times 12 over 51. We'll just write it out for now, and then we'll calculate it later. To get down this branch where you get an ace, but you do not get a face card, that'd be 39 over 51. Over here you get 48 out of 52, and then you get 12 over 51. Even now, when you're multiplying these two, you should recognize, oh, something happened to the universal from one to the other. These are dependent events. Okay. And maybe for sake of time, I will just give you these numbers. So if you multiply the top, you get 48. Just write these down. 4 times 39 is 156 over 2652. 48 times 12 is 576. Page 32, 2652. And the last one is 18 72, 2652. Here's something I always want you to check, and this is how you know you did things right. You make a little line down here, and you will check if you get a 1 or 100%. So if you add 48, 156, 576, all of these up, all the numerators up, you better get 2652, okay? In this case, I do get that, which is 1, which is 100%, okay? That's a little bit of a check, like, am I doing things right? Okay, so there you have it. Do you want the percentages? 1.81%, 5.88%, 21.72%. So if you add up these percentages, you get 100% as well, by the way. Okay. So there you have it. Which one did this question ask for? Mr. Dixon, you're doing a lot of work. This better go somewhere, right? Like this has to get me somewhere. Well, the only branch that shows that you're getting an ace and a face at this, like one after the other, is this branch here, of course, right? So this is the one that answers the question, right? So you would have, let's say you did not do the tree diagram, you should have known, well, the first event is an ace, right? So this is the probability of ace and face, okay? That's what it is. You should have recognized, well, there's 4 out of 52 to begin with. A card has been drawn, not replaced, so therefore I have 51 left. I still have 12 faces, right? And so this is how you would get that answer. But this is really what's in the background happening at all times. Because I could ask you what's the probability of getting an ace and not a face, right? Then that would be it, right? So keep that in mind. So here's the big formula. You know what? This formula looks scary, but it is just saying what we just did here. It's just to prove the point, right? So I would highlight this for sure. Okay. And you're like, why do you always give us 2 versions of the same thing, right? Because it's important to understand that, right? I'm gonna read it to you. It says it here as well. How about I just read it? If you look at the first one, the probability of A and B happening, so face and ace, for example, it's the probability of drawing an ace times the probability of drawing a face card given that you drew an ace in the first place, right? That's what this is saying. And notice that it's a vertical line, not a backslash. So it's not the only, remember in chapter 3, that's very important to remember, right? And what is this one saying? Well, you could have reversed the order. You could have said probability of getting a face card times probability of getting a face card given that you already drew an ace before, right? So you can state the same thing, so you can flip this in any way you want, okay? You should be able to determine, right? How about this? Given that A already happened. We use this when you clearly can tell that that the first event affects the second. You should be able to determine when 2 or more events are dependent by considering whether or not the total possible outcomes is being affected or are being affected, right? Total possible outcomes are being affected. That's when you know something, 2 events are dependent. The key word you will encounter is items are not being replaced. This means that if you draw a card from a stack, you do not replace it. You have 51 cards left. I'm saying the same thing over and over again. Okay. Here's another formula I want you to. It's derived from one of the ones up here. Okay. So let's say you want the probability given that something else already happened. You have to divide the probability of both of them happening by the first event that occurred. Okay. And notice what I say down here. Use this when you're given the probability of both happening and the probability of one of the events, right? That's when you're going to be using this. Not very often, but it does happen from time to time. So let's do a little bit of math so you can wrap your head around this and then practice it. Okay. I'm making kind of a big deal out of it. I think after you do a couple of examples, you're going to know what needs to be done. Okay. So here, page 33. There are 3 green, 2 red, and 4 blue marbles in a bag. You're drawing 2 of them in a row. Determine the probability, right? Answer with and without replacement. Very, very important. I'm going to ask you to do them both side by side, right? With replacement, we would make events independent. Sorry, it's very small there, but independent. Without replacement, right? Dependent. So I'm kind of comparing it side by side. What if it had been an independent scenario or dependent scenario? So 3 and 2 plus 4, we are at 9, right? 9 total. Let's put that down. Oh, you can see that 9 total, right? So picking a green and a red marble, right? You want with replacement, and over here we're going to do without replacement, and that's going to stay the same across this page. Okay, without replacement. So let's look at it side by side. If you replace, then it's just P of green and red is just probability of green times probability of red. Okay, write it down. This is the formula. There's no vertical line in that formula. I want you to make the connections between the two, which is probability of drawing a green. What is it? 3 out of 9, right? And probability of drawing a red, you're putting it back, goes back in the bag, right? So then you still have 9, and there are 2 reds, right? This one can be reduced to 1 over 3, but let's just do 3 times 2 is 6, 9 times 9 is 81. Okay. Let's write it as a decimal and percent as well. So that's 0.0741, which is 7.41%. Okay. Without replacement, we can do this, guys. Oh, this is dependent. So that means that probability of drawing a green and a red is going to be like this. Watch. If you want to go probability of green first, right? Then you have to say, then I'm going to find the probability of red given that you picked a green in the first place because you didn't replace it. You have to, that's the formula, like that's how they're different in the formula, and here you will see how the answers are different when you calculate. Probability of green is still 3 over 9. And what's the probability of drawing a red given that you haven't replaced it? Well, you have 8 left, correct? And how many reds were there again? 2. Okay, so that is all that changed in this case. Okay, so 3 times 2 is 6. 9 times 8 is 72. Okay, 6 divided by 72 is 0.0833, which is 8.33%. Does that answer make sense? Is the probability a little higher? If you think about it, it is. As you're removing, right? As you're removing things from the basket, right? In this case, you still have the same amount of reds left on the second grab, right? So yes, your probability is slightly higher in this case. Okay, 2 blue marbles right here. So with replacement, without replacement, let's make this bar here. So 2 blue, if you're replacing, probability of blue and blue, right? That'd be probability of blue times probability of blue. No news there. We've got 4 out of 9 blues and 4 out of 9 blues again. That is 16 over 81. That is 0.1975, 19.75%. Okay. Now let's do the scenario where you're not replacing the first marble. Probability of blue and blue, you write it like this. Probability that you're grabbing a blue times probability that you're grabbing another blue given that the first was already a blue. Right? So you got to write it out like that. Is equal to probability of blue at the first go is 4 out of 9. This is special. This is going to be a little different than before. How many marbles are left? 8, right? How many blues are left? 3, right? So this is where numerator and denominator are both affected. Okay? So that's 4 times 3 is 12. 9 times 8 is 72, right? This would be 0.1667, which is 16.67%. So there actually probably went down, and it is because you actually took a blue out the first time, right? And now you're trying to grab another blue. So both of them have been reduced, right? Okay, hold on. I want you to try some of these. So I actually pasted the worksheet right into this booklet. So let me just fast forward a bit here. I want you to try, not this one, not 35. I want you to try 36. Page 36 is your homework. Looks like this. Okay, so I'm gonna type in, I'm gonna write it in right here. Homework, page 36 in the workbook. Sorry, in notes. You don't have a workbook. My grade 11 applied class does. Okay, so just try that page. Thank you guys. Have a great day.